Una en vigorita.
Pode conversar um pouquinho depois do almoço e depois também você recebe.
Solving is a little bit too much.
Okay, so that's
Okay, so thanks. So good morning, everyone. Thanks for being here. And today I would like to talk a little about my work, my recent work about dark energy dynamics and massive neutrinos in light of the new data, recent data from the dark energy spectroscopic instrument. This is a work that I've done in collaboration with all of these amazing people, and I'm really grateful to collaborate with them. So I would like to start slowly and saying a few remarks about the Lambda CDM model, which is the standard model of cosmology nowadays. And the Lambda CDM model is built over 4 basic assumptions. The first assumption is that the universe is made of all of the particles that comprise the standard model for physics. But beyond these particles, there are 2 other components in the universe that we really don't understand a lot, which are cold dark matter, which is the CDM, and dark energy, which is in this model is modeled as a cosmological constant. Beyond these species, the Lambda CDM model, or in fact, every cosmological model assumes that after the Big Bang, the universe went through an accelerated phase of expansion, which we call inflation, which is can be realized by a slowly growing slit field. And this model is very successful. So, for instance, it can fit the CMP and isotropies very, very well. This is the blank CMP power spectrum, and the red dots are the data points, and the blue line is the Lambda CDM best fit. So it's a pretty successful problem. One of the unknowns, one of the strange species which I really focus my research is dark energy, which is in the Lambda CDM model is a cosmological constant. Dark energy drives the late time acceleration of the universe's expansion, and its existence is supported by many different measurements. So you can think of geometric probes of the universe's expansion. So you can think of distances and redshifts from standard candles, such as type 1a supernovae, but you can also think of distances from baryonic acoustic oscillations. It's also supported by CMB, temperature and polarization and isotropies, and statistics that we extract from the large scale structure, for instance, from galaxy surveys. And ever since 1998, when dark energy was discovered, the Lambda CDM model has had great success in fitting a lot of independent measurements. However, this success has led to increasingly precise surveys that were designed to measure the Lambda CDM parameters with ever smaller error bars. And this increased precision started to reveal some inconsistencies in the Lambda CDM model. One of these inconsistencies is a very well-known problem in cosmology, which is the Hubble tension. So the Hubble tension is a discrepancy between 2 different types of measurements of this parameter H0. H0 is the current rate of expansion of the universe, and it can be measured by several independent ways. 2 of them, which nowadays yield the most precise measurements of H0. are using the distance redshift relation to nearby astronomical objects, which we call these distance ladder measurements, which are represented by the blue dots, the blue stars, where the star represents the mean and the bars represent the error bars. And also you can always also measure in this parameter independently using CMP measurements, which are these red dots. And as time passed and the surveys got increasingly precise, they started disagreeing with one another. And they started disagreeing by a very large amount, actually. Nowadays, this station has a significance of 5 sigma, over 5 sigma. So this is a very big problem in cosmology nowadays. Another one of these inconsistencies is a lesser known one and a less significant one, involving not H0, but a more subtle parameter, which is this S8. S8 is related to sigma 8. Sigma 8 is the mean amplitude of matter fluctuations inside a sphere of a certain radius, which is 8 megaparsec divided by which. And this parameter, once again, it can be measured independently several different ways. So in the left, for instance, these dark blue dots represent the measurements that were inferred from CMP. So from CMP anisotropies, temperature polarization, and lensing from 2 surveys, so from Blunt and Hatt. And in the right side of this dotted vertical line, you see measurements that belong in this broad class of large-scale structure measurements. So you can see these greenish points are from weak lensing. The orange is a combination of weak lensing and galaxy cluster. The light blue is just galaxy clustering. The red points are cluster counts, and the green points are from redshift space distortions. All of them measure the large-scale structure of the universe in some different ways. And the idea is that the large-scale structure measurements, they are systematically a little bit lower than the CMP measurements. How I'm really sorry about having to turn the head. But the fact is that all of these large-scale structure points, they are systematically just a little bit lower than the CMP measurements. The significance of this tension vary because large-scale structure measurements, they are very sensitive to systematic effects. You can have several different treatments which lead to different values of SA. So this tension may vary. Some of these points are not even in tension with CMB. Some of them have a more extreme tension. So it's not as big as a problem as the double tension, but we are currently heading to stage 4 measurements. So in the next few years, we're gonna have more precise measurements of both CMB and large-scale structure. If nothing happens, these error bars are just gonna get smaller, and the tension might get increased. This is a huge problem, and we're not really sure how to solve these tensions, but they might indicate they might be solved by new physics. Okay? Again, these tensions may be caused by unresolved systematic effects, some effect that either survey or both surveys are not taking into account. But as we failed to solve these tensions with different systematic treatments, people started looking at new physics solutions. So there are infinitely many candidates to tackle these tensions. You can have dynamical dark energy. You can change some aspect about dark matter. You can modify your theory of gravity. You can add interactions between the dark sector and other species. You can add dark energy contribution network combination. You can change the neutrino physics. Then you can. And on top of this, very recently, we have been seeing some interesting, intriguing hints of dynamical dark energy. So a few months ago, in this same meeting, we had a presentation about DESI BAO results from Louis, and we discussed a little bit about this. But the fact is that these hints of dynamical dark energy came even earlier than DESI. So from the end of last year, we had the Union 3 supernovae dataset was released, and they also claim a deviation from lambda CDM, a significant deviation, and also from the dark energy survey supernova. So all of them are distance measurements, distance redshift measurements, and they are all very recent, and they're all pointing towards something that's away from lambda CDM. So in these plots, the lambda CDM is always represented with this crossing of some dotted lines or a dot in the case of Union 3, and the confidence contours. The 95% confidence contours, they always exclude lambda CDM. So this is a very interesting signal that cosmologists have been making lots of investigation. It's a very intriguing result that might show that might be the first hints of something that's not lambda CDM exactly. And I went with the train, I went with the hype train, and this is a very interesting signal. We had to analyze this, okay? So if dark energy is not a cosmological constant, what is it? What is the data telling us? So all of the previous analysis, they relied on these so-called W0 WA parametrization, in which the dark energy equation of state is just a linear function of the scale factor. And this is the behavior that you can take from data. So these left side plots show the equation of state of dark energy as a function of redshift. And what data is trying to tell us is that dark energy had a phantom behavior at large redshifts. Phantom means that the dark energy equation of state is less than -1, meaning that dark energy violates the null energy condition. And very recently, at redshifts around 0.5, so very recent, dark energy, the transitions from having an equation of state that was below -1 to a dark energy equation of state that's above -1. So it doesn't violate the null energy condition. In the right plots, we show the inference for the dark energy density. So with dark energy density, it were increasing up until very recently, up until redshift 0.5, when it started decaying. So this is the behavior, the dynamical behavior that's being preferred by these new data sets. Apart from dark energy, there's also another intriguing question that got raised by DESI data, which is the fact that their data can constrain massive neutrinos, the mass of the neutrinos actually very, very well. So if you combine DESI BAO with CMB data, you get an upper bound on the neutrino field that's kind of approximately 0.07 electrons volt at 95% confidence level. And this is a little bit dangerous because these upper bounds, they from cosmological experiments are getting increasingly tight, and they're getting always closer to the lower bound that's inferred from neutrino oscillation experiments, Catherine, etc. And so if from neutrino oscillation experiments, you can have a neutrino mass sum that's at least 0.05, 0.059 electrons volt if you assume a normal hierarchy, and 0.1 electrons volt if you assume an inverted hierarchy. So the cosmological constraints are already in tension with the oscillation experiments if you assume an inverted hierarchy. And again, in the next years, we're going to have even more precise measurements. So if this cosmological upper bound on the neutrino mass gets more and more constraining, we might have a tension between cosmological constraints on the neutrino mass and neutrino oscillation experiments. And there is this very strange signal that we are getting from cosmological experiments, which is the fact that it looks like cosmological analysis prefer negative neutrino masses. So this plot is not from me, it's from another also recent work, where they explored this idea that they profile the likelihood of the neutrino mass, and they find that the chi-square, the likelihood, has a maximum in negative neutrino masses, which is completely unphysical because the neutrino masses should be positive. That's
Which
much
physics is represented by this plot? It's CMB.
CME and BAO distance measurements. So this all assumes lambda sigma.
How does the neutrino mass would affect the distance measurement?
That's a good question. I think Planck is the data set that gets the most constrained power in this, and DESI just adds geometric information, so it breaks the degeneracies, help constrain the neutrino mass. So it's actually Planck because Planck measures the formational structure. You can measure the lensing of the CMB, so you can measure neutrino mass because the neutrino mass affects the structure formation. If you have more neutrino masses, you are going to have less structure in small scales, and this affects lensing. So most of the constraining power on the neutrino mass actually comes from CMB. They in the DESI paper they never report like DESI only constraints on the neutrino mass sum, because this effect only comes from very early redshifts. But DESI can help constrain because they add extra geometric information at low redshifts. So you can break some degeneracies in the CMB because CMB only probes, mostly probes visits near recombination. And if you add extra geometric information, you can help constrain late time.
So another question. So the DESI, there's no shape of the power spectrum in the DESI measurement. It's just BAO.
It's just BAO yet. As far as I know, yet they might release some other power spectrum data. I think they're gonna have correlations. I don't know if they're gonna go with full shape measurements. I don't know. But this is just from the BAO. It's just from this.
And how are these constraints? But from CMB, it's basically also the shape of the angular power spectrum there. So how is this generated with SMITE or S8? Because it comes from, you're not constraining large scales, it's mostly scales below the horizon at battery quality, right?
Yes,
So it's also the same region where sigma 8 comes from.
yes.
So how is it generated sigma 8?
If
it's at all.
you mean the neutrino mass sum, how it does it correlated with sigma 8 and S8, right? I don't have a clear answer to you. What I can say is that neutrinos, massive neutrinos, they suppress the matter power spectrum at very small scales, at scales that are below the free streaming length. So I
It's
would
not very
say,
small.
uh,
They're not very small. They're smaller than horizon, but that's not.
yes, exactly,
Very small.
exactly. I would say, I mean, I would answer you that the neutrino mass sum, they would decrease the sigma 8 because you are suppressing the structure. So, but I'm not completely sure about it. But I know this effect of suppression at small scale. Okay, so coming back, some people have been investigating this preference for negative neutrino masses, and this is a completely unphysical effect that might call for new physics to solve because we can't have negative neutrinos. Okay, so from all of this overview, we have some questions that were raised by DESI BAO data. One of them is what drives this preference away from lambda CDM and in favor of dynamical dark energy. People claim that there are some outlier points, especially coming from these samples of luminous red galaxies and emission line galaxies. But some people also claim that these new supernova catalogs prefer higher values of omega matter when compared to BAO. And this mild tension, people don't even call this tension, it's just a small discrepancy. It can be solved by dynamical dark energy. So you can see here the posteriors of omega matter from different probes, and you can see that DESI BAO data, which is the blue one, is significantly smaller than the supernova and then the supernova data sets. And the fact is that the more discrepant the omega matter is, the most significant is the detection for dynamical dark energy. So people started questioning these new supernova data sets. But there are also some outliers in the BAO, in the DESI distance measurement. So you can see this yellowish dot, which sits very, very far from the lambda CDM test fit. And people tried just taking out this point and substituting by other distance measurements from other surveys that are in this similar redshift range beam. And they found that the preference for dynamic dark energy also decreases significantly. Apart from this, another question is, can these data sets, like what's the actual shape of this signal? Because all of the previous analysis, they relied on a very simple parametrization for dark energy, which is the W naught W wave. And in principle, we might have a signal that's different from the one I showed before. A signal that's more complex, that's not non-monotonic. So can these data sets detect more complex dark energy dynamics? And finally, what those dynamical dark energy imply to neutrino mass constraints, because the neutrino mass sum is actually correlated with the dark energy equation of state, and phantom dark energy actually allows for higher neutrino masses. So if neutrino masses, they suppress the growth of structure in small scales, phantom dark energy actually enhances the structure because they extend the period of matter domination. So if you have phantom dark energy that increases the formation of structure, this allows for higher neutrino masses that suppress this structure and give it back to this balance. So there is this between the dark energy critical state and neutrino masses. And dynamical dark energy can actually relax the neutrino mass constraints that we get from cosmological probes. So this again is something interesting to analyze, because if we assume lambda CDM, we're heading for a tension between cosmological measurements and neutrino oscillations. Okay. So in order to investigate dark energy dynamics, we consider 3 models of dark energy, which allows for phantom behavior. It allows for phantom crossing, which is the signal that's in principle being detected by DESI data. And I'm going to explain a little bit about these 3 models. So the first one is is just a parametrization of the dark energy equation of state, which is just a transition. The equation of state just smoothly transitions from a value W1 at early times to a value W0 at late times. The moment of transition is controlled by this parameter C. And the speed of the transition, how sharp this transition is controlled by this parameter sigma. So you have 4 overall parameters. And this is just a parameterization that was that aims to probe, like, when does the phantom crossing happen? Do we actually need the phantom crossing? And if so, when did this phantom crossing happen? So another model is a more general, it's maybe the most general parametrization that you can think of the dark energy equation of state, which is just you take a window of redshift where you're interested and divide this window in beams. And then the dark energy equation of state is just going to be a constant value.
But that looks like a rough Gaussian process.
Yes. And people have done Gaussian processes. People also have done. But yeah, this is simpler. This is dumber than Gaussian process. Definitely. But we chose simplicity. We can control the window, the beamings, and we can get some good result with this. So this parameterization is completely agnostic to the redshift evolution of the dark energy equation of state. It's very general, and we test using 5 and 10 beams. You could go further, but by now, we are just adding a bunch of parameters and see if we're detecting things. Adding parameters made the analysis more computationally expensive. So we stopped there. We made some tests with increased number of parameters, but we chose 5 and 10. And finally, another model that we wanted to analyze is monochromic K-essence model, which is essentially a scalar field, but it's not a canonical scalar field. So it's Lagrangian. It's not. It's Lagrangian. It's defined as this P function, which is a function of the scalar field phi, and the kinetic term, which is this x. But it may be a more complicated function. It's not just the kinetic plus the potential, is something that's more abstract and more complicated. So we took this model from literature. So this P function is given by this expression, that's P times minus x plus x squared, and V is it's not a potential, but it's a function that depends on the scalar field, and it's an overall scale of the Lagrangian. And it this model is interesting because it can cross the phantom barrier and it produces an oscillating equation of states. These are some examples where I'm varying one parameter at a time. So this alpha parameter controls the mean value of the equation of state. The A parameter controls the amplitude of the oscillations, and the nu parameter controls the frequency of the oscillation. If the frequency is very, very small, the field might not have undergone a full oscillation during the whole cosmological history. And yeah, but this is essentially the equation of state, the equations of state that we're probing. Okay. So to constrain these models, we are going to combine geometric information from CMB, BAO, and supernovae. So these three data sets have lots of synergies. First, because they probe geometry for different redshifts. So CMB, you're probing the distance to the last scattering surface, which is around 1100. And you're also probing the sun horizon at that redshift. So that's good geometric information at high redshifts. But we also have DESI BAO data, which is some 20-ish points from 0 to redshift 4.2. And finally, we have these different supernovae data sets that we have many measured supernovae, but they are restricted to a redshift range that goes up until 1.2, 1.3. So these three data sets, they have lots of synergies because they cover different redshift ranges. They are independent measurements, and they can put some good constraints on the dark energy dynamics. For the supernovae data sets, we are looking for different. Well, the first of them is this quote unquote old Pantheon data set that has a 1024 supernova. This data set is interesting because it prefers an omega matter value that actually agrees with DESI and Planck. So it's a lower omega matter value, so it might not detect any dynamics for dark energy. But we are also using the most recent state-of-the-art supernova data sets from Pantheon Plus, Union 3, and Dark Energy Survey Year 5. They all have more supernovae. They all have more robust modeling, robust light curve modeling, extinction, dust removal, all of these more fancy techniques from Pantheon. But they also have a higher omega matter value that can trigger these detections for dynamical dark energy. With these models and this data, we prefer model selection techniques. So which of these models are able to fit the data set better, how this fit compares to lambda CDM. And so we maximize the posterior and find the minimum chi-square for each one of these models. So models that fit better are generally preferable, but in the case of the BMW model, we are actually throwing so many more parameters that of course we're going to fit better because we're just adding like 10, 15, 20 parameters. So more general models can data better. So we also need to penalize models that have more parameters. And we also assess neutrino mass constraints, not assuming lambda CDM, but actually assuming other dark energy models. So we're going to assume, apart from lambda CDM, we're going to assume the W0 WA and the beam equation of state model. And the thing is that if we have neutrino mass constraints in the beam model, we are actually marginalizing over the dark energy dynamics at late times, which is interesting. And let's go for some results. So for the transition model, we see that all data sets prefer an early equation of state that's phantom, but Pantheon doesn't prefer the current equation of state under the Pantheon data set agrees with lambda CDM. For the other data sets that prefer a higher value of omega matter, you can also see this panel of W0 versus omega matter. The data sets that prefer higher W, they also prefer higher W0. So this is one of the points that's in the heart of this detection of dynamical dark energy. And if you use a supernova data set whose omega matter agrees with DESI, you actually don't see a deviation from lambda CDM. The redshift of transition is weakly constrained, but generally they prefer something around 0.6. The posterior peak at around 0.6. And again, this is just the confidence contours. We can translate this into a reconstruction of the dark energy equation of state, assuming this model. So you can see that if we use Pantheon, which is this first row, you actually, like lambda CDM, which is just these horizontal dashed lines, lambda CDM is actually not really excluded. Whereas for the other supernova data sets, you can see that the current equation of state, the W at C0, is significantly above -1. So this is interesting. But overall, this whole analysis using this model agrees with the results, assuming the W not W. For the general beam W of C model, we just show the constraints on the parameters. You're just gonna have these huge error bars that may not tell you a lot, especially in the panel, in the right panels where we use 10 redshift beams. So in principle, you cannot extract a lot of information from this, but we are already seeing some interesting effects in the left panels, especially if we are seeing the first 3 rows. We're actually seeing an increase on the equation of state from the first to second beam, and then a decrease from the second to the third. But again, this is a lot of it's very difficult to interpret these constraints because the error bars are too large. We added a bunch of parameters. They are correlated. We can see the correlations from this plot. So it's not trivial to conclude anything from this.
Line is what?
The best fit from W not WA, because we wanted to see if we use a more general dark energy model, if this agrees with W not WA. So do we need something that's beyond W not WA, or is just W not WA enough, right?
So there's no clear feature that makes you think that there is a larger WA.
Exactly. We're gonna get to that. But again, from this reconstruction, from the constraints on the parameters themselves, it's difficult to interpret. So what we did with this sample, with these results, is we've done this technique that's called the principal component analysis. So we ran Monte Carlo Markov chains to sample the posteriors, right? So when we run these MCMC, we have a lot of samples of the dark energy parameters. If we have these samples, we can calculate the sample covariance matrix of these equation of these W's. And since the covariance is real and symmetric, you already think of diagonalizing. So when you diagonalize, you find a basis of eigenvectors that that diagonalize the covariance. So in this basis, the correlations vanish, which is good because in that other plot, we couldn't actually see the correlations, but they were there. And now we're actually going to transform these W's into other components that are uncorrelated, which are these physical. So instead of having W's, we're actually expressing them as a sum in another basis, which is this basis of principal components EI. And the amplitudes of each principal component are these alphas, which are the things that we are going to constrain on the end. So just out of curiosity, these would be the eigenvectors of the covariance matrix. You can think of these as different excitation modes of the dark energy equation of state. And all of these modes are independent from one another in the sense that they are not correlated, okay? And these are some constraints on the amplitudes of each principal component. So each of these amplitudes is gonna multiply one of these eigenvectors and then be summed to get a final evolution of the dark energy equation state. And what we observe is that some of these principal components, their posteriors actually deviate from zero. Here we can show the 1D posteriors because all of these alphas are uncorrelated with each other. So this is already a good picture of the dark energy constraints. And some of these components, they actually deviate from zero, which would be the lambda CPM. The first alpha is the component that's related to a thawing behavior. So if we go back, we can see that the first eigenvectors is something that is zero at high redshifts, but as you decrease the redshift, these components, they start increasing. So this would be a thawing behavior. And this is a behavior that's not detected with Pantheon supernova. So the black Gaussians of alpha 1, they're all centered at zero. But assuming the other supernova, the Gaussians, the mean of these Gaussians, they start increasing away from zero. This is similar to what happens with W not W, and this is caused by the tension in omega matter between DESI and the new supernova data sets. But apart from this, in the top row, you actually see that this alpha 3 component is actually, for all supernova, it actually deviates from zero. All data sets actually prefer a negative alpha 3 in the top row, which is the 5-bit scale.
Sorry, what's the shape of this?
Yeah, sorry. These are big pictures, so it's difficult to show them at the same time. But we're looking at that in the left column, the middle row. So that E3 over there, that's the shape.
Okay, so basically something happened at shape 0.5.
Yes, exactly. And this is related to that feature that we see in the second row in the left column, which is something that's in the second and third redshift states.
Sort of oscillation.
Sort of oscillation, exactly. And this is This is actually preferred by all of the supernova datasets, even Pantheon. And we actually saw that this preference is actually driven solely by DESI. So this is just DESI that drives this preference. For 10 beams, you actually can see that two of these components are preferred by data rather than CTP, which are the components alpha 4 and alpha 5. It's not unanimous for all supernova, but DESI 5 and Pantheon Plus, they like this alpha 4. So you can see the green dashed and the purple dotted away from zero, where the black Gaussian and the dashed dotted orange in the alpha 5, they're very away from zero. So it's not unanimous, but they kind of represent similar oscillating features. And one of the ways that we can see this is to actually reconstruct the dark energy occasional state, not using all of the principal components, but just the principal components that are quote unquote detected. Just so we can get rid of all of those error bars that come from the very generality of the model and just see the behavior that's being, the features that are being preferred by data. And this is what we do here. We reconstruct the equation of state only considering the principal components, the features that that have been detected. So now you can see much more clearly. Of course, this isn't the full picture because we are actually setting by hand a lot of parameters to zero, but it shows the behavior, the non-standard behavior that's being picked up by data. And of course, you can always devise some parametrization or fundamental model that has these shapes, and these models would be detected by data if they correspond to these shapes. So it's sort of oscillating, and we uncover these oscillating features that can't be picked up by a monotonic parameter. So this is interesting. This is something that's not standard, and that's something that's away from the research. So these are the features that the data prefers. Of course, we're showing them in this maybe tendentious, maybe biased way, but yeah. And finally, the results for the k-essence model. So the first thing that we saw is that we had a frequency parameter, and the frequency goes into a sine. So we saw that when we run the Monte Carlo Markov chains, we saw that the posterior is multimodal. And you can actually run Metropolis Hastings with multimodal posteriors. So what we did to avoid this term is that we minimize the likelihood of fixing the frequency parameter to several values. And we ran Monte Carlo Markov chains by fixing the frequency to the values that overall minimize the chi-square. So it was very interesting because we found that all of the different supernova data sets, they refer the same frequencies that have these values of 10, 24, 30, and 38 in Planck masses inverse. And then we just fix these frequencies and let the amplitude and the mean value of these oscillations vary in the MCs. And these are the posterior distributions. Again, just as a reminder, alpha controls the mean value of the oscillations. 0 corresponds to oscillations around -1. And what we would like to see is a preference for alpha greater than 0. which would represent the presence of oscillations, right? See that especially for these higher frequency values of 24, 30, and 38, you have a mild to significant preference for oscillations. For the higher frequency values, the preference is not big, but the posteriors are compatible with big amplitudes. We think this is because if we have high frequency values, the energy density is an integral of the equation of state, and the Hubble parameter is an integral of the density. Sorry, the distances are integrals of the density. So you are actually averaging over all of these fast oscillations. So the parameters that they get they get wider, but not really excluding zero oscillations. And to visualize the preferred shapes of W of Z, we take some of the MCMC samples and we color code them by the improvement in the fit compared to lambda CDM. So the darker lines, they represent evolutions of the equation of state that are better than lambda CDM by that amount. Okay, so yeah, and this is what we see for KS. These are the preferred evolutions. Finally, we compared the goodness of fit. We compare how these models can fit the data sets better than lambda CDM. As we expected, the overall winner, the overall model that has the biggest improvement in the chi-squared is the model that has more parameters, and you can't really avoid that. And the difference between the most general 10 means WC and W0WA is very significant. But you always need to penalize models that have an increased number of parameters. So there are two ways to do that. One is to turn those values, those delta chi-squared values, into a z-score that you get from a chi-squared distribution, and then you get something that's kind of a statistical significance, but we are not really claiming that's a statistical significance of detection. We're just comparing these. Like the z-score is just a quantitative measurement of how a model fits a data set better and has less parameters. But we also use the Akaike information criteria. And these two model selection techniques, they have the same conclusion, is that W0WA is the most economic model for these data sets. It's the model that can bring the most improvement to the fit and also has a more simple distribution, a more simple parameterization, because it only has two parameters. And finally, neutrino mass constraints. Each of these different panels represents a different combination of data sets. Each row represents a different CMB data set, and each column represents a different supernova data set. And each line represents a dark energy model. And overall, we see that W0WA is the model that usually provides the most relaxed constraints on the neutrino mass sum. But when we analyze the beamed models, which are more general, so these constraints are actually marginalized over all of the parameters, you actually find that the upper bounds, the upper limit on the neutrino mass sum is a little bit, well, not a different lines. The different lines represent constraints assuming different dark energy models. So black is lambda CDM, green is WNW.
No, they got the
Oh,
horizontal lines.
sorry, the different rows.
Rows.
So the different rows represent different CMB data sets. So the first row is Splunk. The second row is we change Splunk to ACT CMB data. And in the third row, in addition to ACT data, we include CMB lensing. And CMB lensing adds extra information about structure because it's the lensing of the
It
CMB.
looks like the main constraining power, highest constraining power.
Yes, yes. Actually, the Splunk has higher constraining power, but there are subtleties because Splunk has a lensing anomaly. And this lensing anomaly actually drives very tight constraints on the neutrino mass sum. This is why we changed Splunk to ACT. And Splunk and ACT are CMB data sets that have similar constraining power, but ACT doesn't have this lensing anomaly. And you see that even though they statistically have the same constraining power, because ACT has no lensing anomaly, it provides it provides relaxed constraints on the neutrino mass sum. So it's not about statistical constraining power. It's about this weird effect that's present on the Planck data set and it's not present on ACT.
So really different. Can you use Planck 2020?
Yes, and people have, and we actually should because Planck 2020 has no lensing anomaly. But instead of using Planck, we actually use ACT. People had already published some papers that study this very carefully with the different Planck data sets, but they never use ACT. So we thought that was a good opportunity for us to like not repeat what's already in the literature and just use a new data set that people haven't studied yet. And we got the same results. And it's not same, but qualitatively it's the same results because the new data sets, they also relax these constraints on the neutrino mass when compared to the 2018 original likelihood. So yes, you can. And in fact, I think you should, but we chose that.
But would it be interesting to compare ACT and Planck 2020?
Yes, we are working on that. We're actually working on that. And these are all something that we're currently working on is that all of these constraints are Bayesian constraints, so they depend on priors. And we want to make these neutrino mass constraints not by a Bayesian point of view, but by a frequentist point of view using profile likelihood. So yeah, this is something that we are looking at, and we're definitely gonna use the Planck 2020 likelihood. But we found that when you actually assume the more general dark energy model, you get slightly more restrictive upper bounds on the neutrino mass sum. It's still relaxed when you compare to lambda CDM, but not much more relaxed. So yeah, I think this is it. This is what I had to say. We investigate some of the questions that DESI data raised. The preference for dynamical dark energy, whether we can see some signal that's less than WNWA, and what does this dynamical dark energy imply for neutrino mass constraints. And we found that even though the difference in omega matter between DESI and supernova data sets, they improve the detection of dynamical dark energy, there's still some preference solely due to DESI data, especially in a kind of oscillating non-monotonic signal. And finally, if we assume the very general parameterization for the dark energy freedom of state, we get slightly tighter constraints on the neutrino mass than those assuming W not W. So yeah, this is it. So thanks, and please, if you have any questions or comments.
Properties that your vision.
That's a good question. So you have the CMB temperature power spectrum. It has that. So actually, let me get to the first slide. So because we actually have the CMB, right? It has this distinct shape, right? So this a lot of physical effects go into these blue lines. Well, make it bigger. A lot of physical effects go into the calculation of this blue line, which is the theoretical interpretation. And one of the effects is lensing. So lensing is essentially the lensing of the CMB photons by the large scale structure. And what this lensing in practice does is it makes these peaks and troughs smoother. So the peaks get a little bit lower and the troughs, they get a little bit higher. So these oscillations essentially get a little bit damped by this, by the lensing. And the CMB lensing anomaly is a problem in the Planet 2018 dataset that if you have the lensing of the CMB dataset that's detected in the CMB dataset is higher than the lensing of the lambda CDM model that fits this dataset the best. I don't know if this is the clearest explanation, but this blue line is the best fit. It's mapped to a cosmological model. This cosmological model produces a structure. This structure lenses the CMB, but the lensing of the CMB from the best fit model is less than the lensing that's actually present in the data set. How do they even know this? That's a good question, but I know that they actually, one of the ways that this anomaly gets very clear is when you add one parameter by hand, which is a parameter called a lens, which is a completely phenomenological a posteriori parameter that just cranks up the lensing. So it's like you're artificially increasing the power of CMB lensing from your model. And when you see the posteriors of this phenomenological parameter, you actually see that this parameter deviates from one. One being the standard lensing, nothing changes. And the posteriors of this parameter are higher than one by some 2 sigma. So this is the Planck anomaly. I don't know if this is the best explanation. You can actually see, like, there are hundreds of papers talking about this Planck lensing anomaly.
So you're not going to try gas and process ever.
I wanted, but people have already by now.
And the results are probably compatible against yours.
Yes. Yeah. One of the Gaussian processes, they actually one of the things that they do is they do Gaussian process not on the equation of state, but on the Hubble parameter. So they reconstruct the Hubble, and it's kind of compatible with this non-monotonic behavior that we see. So they also detect some sorts of oscillations. I never checked if this is compatible with this. In principle, it should be. These results from my work against the Gaussian process reconstruction of the Hubble parameter from other. But I would really like to try reconstructing using Gaussian processes, just for fun.
Sorry, I mean, sort of outside of what is the neutrino? What is the neutrino equation of states? The primordial cosmological neutrinos, which oscillate with these odds and an equation of states, or is it something different?
Sorry, can you repeat your question, sir?
I mean, you talked about neutrino mass constraints.
Yes.
And you talk about the equation of state. The equation of state is that of massless particles. So
No, it's
you
I mean
or
depending on the mass, it transitions from a third to zero,
of course.
and when the temperature hits the mass, right? So we always assume massive neutrinos. We are not playing with massless here, but the equation of state transitions from a third to zero at a point where the temperature is equal to the mass, roughly.
But this is very close.
Depending on the mass, depending on the mass. Depending on the mass. I think.
Oh, I see. So this is physically like a physically like this. Thanks. And oscillations don't play any role.
No.
So that's an João. Yeah, so we're going to be able to talk today.